So now we know what we would like to calculate. Let's go ahead and calculate it. So the amplitude that we're interested in, we start with a particle at the position x is equal to 0. So this is where we release our particle. We then let it evolve for a time t according to the Hamiltonian that we've chosen. And then we want to calculate the probability amplitude that we detect the particle at position x. So we project the state onto ket vector x. So this is the probability that we release the particle from x is equal to 0. We let it evolve for a time t. And after it's evolved for a time t, we work out what's the probability amplitude for it to be detected at position x. So this is what we want to evaluate. Okay, so the operator that's sitting in the exponent looks rather complicated. So what we are going to do is we're going to simplify this by using a relation from quantum mechanics known as the completeness relation. So I assume that you are familiar with this. If not, you need to ask questions and do a bit more reading. What the completeness relation tells us is an identity. It says that operator 1 acting in Hilbert space is equal to the sum over a complete set of eigenstates. And I've chosen to insert here momentum eigenstates. And we'll see why that's a good idea in a moment. So using the completeness relation, I can rewrite this as bra x e to the minus I ht. Now I'm going to multiply by 1, which doesn't change anything. And then I have ket x is equal to 0. So that's the expression that I would like to evaluate. Okay, now let's just remove the completeness relation from here. Now, what is this equal to? So first of all, nothing else depends on p in this expression. So I can pull the integral d3p up front. Then I've got bra x e to the minus I ht and ket p. And then I've got bra p x is equal to 0. Okay, now let's look at each of the elements appearing in this formula in turn. The first thing that I want to look at is this last factor over here. So, I know what xp is. How do I work out what the bracket between bra p and ket x is? Well, I know that this is nothing but the complex conjugate of the bracket between bra x and ket p. So I know that that's true. And from equation 2 above, I know that this is equal to e to the minus I p dot x over 2 pi to the 3 over 2. It's complex conjugated. So all that's going to do is change the sign. Oh, sorry, the sign was a plus. It'll change that sign to a minus I p dot x over 2 pi to the 3 over 2. And we don't want this for general x. We actually want it when x is set equal to 0. So setting x equal to 0 in this expression, let me just maybe write that exponent a little bit more clearly. Maybe this is not written very clearly at the moment. This is minus I p dot x. And plugging x equal to 0 in that expression, we just get 1 over 2 pi to to the 3 over 2. So that's what the underlying term is going to be. Okay, so let me remove all of this. We don't need it anymore. And let me write down what we've got for this piece. This is 1 over 2 pi to the 3 over 2. Very good. Okay, so now let's go and take a look at that matrix element that we've got sitting there. Okay, so we are going to look at this matrix element sitting here. So as a first step, what do we get if we have e to the minus I ht acting on p? So that we would like to know. Okay, well, for h acting on p, we know what h is. This is the square root of operator p dot operator p plus m squared on ket p. And the rule that should be familiar to you from your quantum mechanics course is that if you have a non-trivial function of an operator acting on an eigenstate, the eigenvalue gets plugged in for the operator. So this would be equal to p dot p plus m squared on p. Okay? And what did I use? So let me say it as clearly as possible. If I have some eigenstate, let's say of some operator v, okay? So it's got some eigenvalue, let's call it lambda v on v. I'm using the fact that any function of the operator acting on the state v is just a function of the eigenvalue acting on the state v. So you just plug in the eigenvalue everywhere where you see the operator, and that's what I've done. So I had operator p dot p. That's why they're capital P's there, they're operators. On the next line, they're little p's because I've simply plugged the eigenvalue in. I want you to see if you can prove this rule. You should be able to. If you can't, look it up, because that's, again, an extremely important result that you will use again and again. Under what conditions does that result hold? And can you prove it? So that's a nice exercise for you. Okay, now let's evaluate what we were after. So we've got e to the minus iht acting on p, and it turns out that p is an eigenket of energy, and we can see its eigenvalue is just the square root of p dot p plus m squared. So what should I do? Take the function of the operator and plug the eigenvalue in for the operator. So we'll get e to the minus I square root of p dot p plus m squared multiplied by t, and then we still have the eigenket sitting there. Good. Okay, now what do we actually want? We're close, but this is not quite it. We need to take bra x onto e to the minus iht, ket p. And now we know, well, the eigenvalue we can just pull out. So I'm just going to pull out the eigenvalue. And then we've got bra x on p. So one way of thinking about the equation that I've just written down is that I took this equation that I've just underlined, and on both sides, I multiplied by bra x. On the one side, I cannot take bra x through the exponential e to the minus iht, but on the other side, of course, I can take bra x just through this number, no problem. And then I get the overlap between x and p. But the overlap between x and p is given by equation 2. It's just e to the ip dot x over 2 pi to the 3 over 2. So we land up with e to the minus I square root p dot p plus m squared t plus I p dot x over 2 pi to the 3 over 2. Good. So let's put that in. This is e to the minus I square root of p dot p plus m squared t plus I p dot x over 2 pi to the 3 over 2. And now we don't need any of this stuff sitting at the bottom, so let me remove it. Okay, I guess I'm clear space. It's just a big deficit stuff here. Okay. So we know the different elements of this formula. So now let's just summarize what is the final result. Okay. Here's the final result. X e to the minus I h t x equal to 0 is equal to, well, we'll have an integral d3p. We need to do that integral. We've got a 1 over 2 pi cubed times a 1 over 2 pi 1 over 2 pi to the 3 over 2 times a 1 over 2 pi to the 3 over 2. Well, that's just a 1 over 2 pi cubed. And then we've got an e to the minus I square root of p dot p plus m squared times t plus I p dot x. And this is the answer that we were after. We have now calculated the probability amplitude that a particle that is released from x is equal to 0 and allowed to propagate for a time t. We've calculated the probability amplitude that that particle will be detected at position x. Great. So now we need to turn our attention to evaluating the integral over p and interpreting the result.